in the meanwhile, because I had a question how the electrodes are counted, so I firstly created also physical montage. I don't know. Yes, you can see it. So these are all the holes, let's say, from the montage that you already saw. And I added the electrodes. So as I told you, from the left side, first row. So this would be the number 1, second one, number 2, number 3. Then going back, number 4, number 5, 6, 7, 8, 9, 10, and so on, up to 16. So now I will start sharing my screen again. Share screen. This one here.
I can see it.
Okay,
And
thank you very much, Christoph. Yes, thank you very much. Previously I've managed to define all the electrodes already, all the 16 electrodes that I was on the cap right now. And I've mentioned in the introduction that we can define also different source derivations. Okay, so for the source derivations, we have different options like bipolar. This is for doing bipolar recordings, local average reference, Laplacian, small or large Laplacian, and I will explain you in a bit what is large Laplacian, common average reference, and weighted average reference. The most used, at least for motor imagery right now, we will use the Laplacian reference. So in order to do a Laplacian reference, I will select the Laplacian. I will give it a name. So I will do for C3 and C4. These two electrodes are overlying the right hand and left hand sensory motor areas. Okay, and hand projection. The right hand it's for C3 and the left hand it's for C4 in the contralateral part. So I will make these two electrodes as primary electrodes, and then I will create the Laplacian, the small Laplacian derivation, basically. So C3, C4, Laplacian, a suggestive name, and we'll add it. So this is the constellation name. Yeah, it is a source derivation. So first, in the primary electrode, I will add the C3. We'll click. So we have it in the primary electrodes field. And now we'll start adding the secondary electrodes. So it is a small Laplacian because there are only 2.5 centimeters in between these electrodes. For large Laplacian, it's the distance, it's almost double, almost 5 centimeters, okay? So if I would like to do a large Laplacian, I will take F3, T7, P3, and CZ for this derivation, but I will do it small, so I will add FC3, C5, CP3, and C1. I will do the same thing also for the C4 electrode. I will add it to the primary electrode list and add to the secondary FC4, C2, CP4, and C6. Okay, basically now I created this montage and I will save it because we will use it a bit later. Save montage as plus 16 channels. Okay, now that I saved it, I can close the montage creator. We already see it in here. And I can clear the screen. So as I mentioned earlier, g.BSanalyze has the option to provide also batch processing of some files. This is why right now I will create a new script and I will save it, offline script, offline processing script. And because every single function that I will call from g.BSanalyze will display in MATLAB command window all the text, so all the commands and the command arguments that we can copy and paste, and we can call it afterwards directly from the code. Okay, not from the GUI. Now let's go back to the GUI. So I will load a Motor Imagery dataset. So import cover X. I will take, let's say, this one here. We have to wait one moment until it gets loaded. Okay, now all this file is loaded. So we cannot see too many things in here because, yeah, if I'm setting the scaling to auto, we cannot see a thing if it's how it was loaded. So all these files have a lot of DC offset. And that's why when setting everything to every single channel scale, we see only a flat line. And first of all, so we have the 16 channels of data, as in the montage that we just created. And we have also the 17th channel, which is a validity channel that we do not use in this processing now. So I will just exclude it. So from transform, cut trials and channels, and I will exclude exactly the last channel, the 17. Okay, and stop. Now, the next step would be, of course, we want to see all these data sets. So let's apply a filter. In g.BSanalyze, you can define different types of filters. So we go to pre-processing filter. Okay, so we already have a predefined list of filters in here, but I want to create a filter, more specifically a Butterworth filter, a bandpass, Butterworth. And in Motor Imagery, we usually filter the data in between 8 to 30 Hertz. So the lower cutoff frequency will be 8 Hertz, the higher one will be 30 Hertz, and the filter order fifth. Okay, and I will call it field 830, something like that. We'll add it to the list. It's in here. We'll click OK, and it's automatically popped up in here because it was just assigned. And just click on Start, and all this data will be filtered. As you saw also earlier, at the very beginning, we have this drifts. But yeah, now we can apply the scaling to see the whole data set. So start channel 1 and channel 16, and the scale plus minus 100 microvolts. So now we see them all in here. And here we go. It looks like the data set is very, very clear. So while scrolling through it, we can see also a first marker, which is written in here left. So since it's a motor imagery file, this is for left-hand motor imagination. If we go further, we see also right, and so on. Okay, so the first part is done. I told you earlier that we do need also the montage for this. Let's load also the montage. So header, geometry, and we'll browse for the montage. This is the one. Okay, now after I loaded the montage, we can see that it loaded the channel names, all of them, numbers, and the XYZ positions, okay? Which are very, very important for what we will do next, especially for displaying results, for CSPs, and so on. Okay. And not only, right now, when I loaded this montage, we loaded also the constellation, the source derivation that I defined earlier. Okay. So I will just go further. Next step in here, it's triggering the data, all this data. So As I showed you, we have these markers left and right. So we will trigger this dataset based on the markers. Transform, trigger. Okay, we'll move this to the center. So in the upper part of the window, we have the trial parameters. So basically we have the time before the trigger, which is usually used for as a baseline for other computations, and time after the trigger. The trigger in the motor imagery case is the moment when the cue appears on the screen, the cue indicating the user that he has to start imagining the right hand, the left hand, or feet. It depends on what type of motor imagery he performed. Okay, so before the trigger, I will take 2,500 milliseconds. Okay, and after the trigger, I will take 5,500 milliseconds. We can see that we have also the number of samples for all this. So we have the option to trigger the dataset based on a physical channel. So we can have the last channel, for instance, a channel with some peaks, with different numbers and so on, and we can address it from here. Threshold voltage, threshold level, slew rate, and so on, or markers. So as I showed you, we already have the markers, and let's go based on the markers. So we have the right trials and left trials. First, I selected the right trials, and I will add the name here to be right. And add to list, and then the left trials, and add to list. Of course, we can change the colors and so on. It's not our point today, but very important is that we can also take a data set and split it into different small trials or different epochs. So the last option, which is lineup trials, just splits the data set into multiple trials of a certain length that we specify in here. And that's all. Of course, we can have also an overlap, but for now, I will just trigger the dataset based on these two markers. Okay, and start. Okay, now the dataset is triggered. We see only the trials in here. And in the meanwhile, because I do not want to forget, is to take the code from here and to paste it into the recently created file. Okay. So this code is ready to run directly. If I load again the dataset, or it loads it automatically, but I can kick out all this part. And if I load the file in g.BSanalyze, just add the global variable in here that where everything is stored. But I will show you all this a bit later. So this is the trigger part. Okay, coming back to g.BSanalyze. From this point, I will save this dataset to be able to reload it later, because I will do some other things. I will try to show you different things like spectrum, event-related desynchronization, time curses, and even event-related ERD maps. Okay, so I will save the file, save as triggered dataset, and we'll go on. Now it's saved, it's written also in here. So first, I will apply the source derivation that we discussed a bit earlier. Preprocessing source derivation. So it already has the type of source, C3, C4, that we defined earlier, the Laplacian reference. And I don't have to do anything else but to replace the involved channels. These are the options we have. Add the new channels, so it will keep all this data and add the newly created or calculated channels in the end. Replace only the involved channels, which will be the C3 and C4. C3 it's number 5, C4 is number 8. Or to replace all channels, and we will have only 2 channels in the end. So For this moment, for this demo, I will just replace only the involved channels and we'll click on start. Now I will increase a bit the scale so you can see it better. You can see already in here that C5, that C3 electrode and C4 has a Laplace marker. So we know that it's a Laplacian channel. So header, view scaling, I will increase a bit the scaling to 1 to 16 to 50 micro. Okay. So we can see them better. Of course, you can see that all these channels, these two channels look very nicer. So what it did, the Laplacian reference, it did the mean of the channels that I selected as secondary electrodes and subtracted that mean from this electrode. So this is what the source derivation did. Okay. First of all, let's see the spectrum for these two channels, for C3 and C4, but specifically for the trials they were assigned. Okay. So I will go to Analyze and Spectrum. So in this case, I will use the length of intervals to analyze of 1 second. Because we do have a baseline, I will compare this action interval with the baseline here. So the reference interval starts at 500 milliseconds and it ends at, let's say, 2500. It ends up exactly here. Okay, so compute and panning window, and let's select, very important, selecting the C3 first, which is channel number 5, and C3, it's in here, so it corresponds to the right hand imagination trials, and I will include only right and C3. Okay, and start. Okay, here we have the event-related, we have the spectrum in here. We cannot see almost nothing in here, so let's switch the scales a bit. In terms of frequency, I will cut everything to 40 Hertz. Okay, and we'll go to Y scaling. And I will make it linear so we can see it better. Okay, so here we go. This is the spectrum. Let me set it also to auto scale. Auto scale. Okay, as we see that I filter from 8 Hertz everything before it's cut it out. And after 30, again, everything is out. So the green solid line, it's the spectrum of the action interval that started from second to 2.5 till the end. And the blue one is the spectrum of the reference. So we can clearly see that there's a huge difference, especially at about 11 Hertz. Okay. So this is for C3. Let's do it also for C4. Right now I did all the settings. I only have to select the other channels. So the C4 is channel number 9. So I include only channel number 9 and include only the left trials. And okay, let's start. We'll do exactly the same settings also now for visualizations. So from 0 to 40 Hertz on X scaling, on Y scaling, linear because it's better to see, and auto scale. Okay. Here we go again. Also in here only for the left trials for the C4 electrode. Again, we can see that there's a big difference in between the two action intervals, in between the two spectrums. Okay, So this was the first step, the spectrum. I don't want to save them, I'm just closing them. And we'll go further to the ERD time courses. So I will go to Analyze, and we have event-related desynchronization here. So as settings, the start as earlier, the reference period starts at 500, and the end I will set it now to 2000 milliseconds. Okay, and I will design another filter. Let's say an FFT filter, band pass from 10 to 12 hertz, 10 to 12. And I will call it alpha 1. Add to list. Okay. It was already in there. Sorry, didn't pay attention. Okay, now going further in terms of settings. Okay, so averaging, its mean, factor 16, sign test, and I only have to select the trials. And let's do it again for channel C3. Okay, so it's channel 5 with right hand trials. Okay, and start. And here we have the ERD time course for the C3 electrode while performing imagination. So as you see in here, we have a good difference. Up here, we have a significance level. And we can see that in here down in time from second 4 to 8 of the trial, the event-related desynchronization is pretty strong. Let's do it also for the other channel. For the left-hand trials, so I only have to select the other channels, so include only left trials, and I think it was the 9th channel. Yes, it was the 9th channel. Okay, and start. And again in here we see very nice desynchronization also for the other hand. That's good. That means that the data, the user was very good in performing motor imagery. So I will close these two ones now. And I will go forward to the ERD maps. So it's from the same menu, analyze ERD maps. And again, I will set the reference, the start reference at 500 milliseconds, the end of reference at 2000. Okay, so lower frequency bands, border 8 hertz, upper 30, bandwidth of single bands 2 hertz, step 2 hertz. Let's not take one by one. Okay, and I will do the same for, first of all, C3, which is in channel 5, and right trials. Okay, and start. And here we have a very strong activation from second 4 in this band starting from 8 hertz. So this is the 8 hertz band, 10 hertz. In 12 hertz band, we have, it's a bit smaller, but also in beta, you can see that it's pretty strong. So this is for C3. Let's do it also for C4 for the other hand. So only select trials, include only channel 9 and include only left trials. Okay, and start. Ooh, again, also in here, for the other hand, the activation is very, very strong. So the EFDs are with hot, with red, orange, red, and event-related synchronization are with blue. But in here, we only checked the EFDs. So from my point of view, it looks very, very good. So as I said, this subject will have a very good accuracy in controlling the motor imagery-based BCI system. Okay, I don't want to save it. I'm just closing it. So this was only to show, this part was only to show you how to investigate the EODs and the EOD maps and also the spectrum. This is why I saved earlier this test dataset. So I can reload it, because from here on, I will do the processing, the normal processing of a motor imagery file, okay? So I will reload the file from where we left, the triggered dataset. And I will do the common special patterns processing and so on. So I will show you exactly how to create a spatial filter and how to apply it, extract features, and then to create a classifier and to classify a dataset. Okay, so first analyze CSP, common special patterns, and I will select the class right as class 1, class left as class 2, and I have to specify the CSP data window for creation. So I will take 5,000. So I will take a segment of 2 seconds from second 5 to second 7, because that's the point where we have the best ERD, as we've seen earlier. And I will save the results because I do need to use them in a bit. So it's CSP filter, and we'll start. Now we will see also the CSPs. Okay, so here we have them. Look in here, I don't know how well you can see it on Zoom, but in here with very small dots, we have the electrodes, with the electrode numbers, as I showed you earlier. And this spot in here corresponds to the C3 electrode. This one here should correspond to the C4, but it's a bit lower, probably due to some artifacts. So the common spatial pattern method is very sensitive to artifacts. Basically, I haven't did anything to the data set except filtering it. Usually when creating a CSP filter, you have to investigate and you have to make sure that there aren't any artifacts, any movement artifacts in the data. So as soon as you created the filter, you can make sure that, okay, if you create it from a very clean data set, from here on, it is almost immune for the artifacts when classifying something. So just to show you, just a small parenthesis, we can have a look through the data set. I will add in here 2 trials at the same time. Maybe there are some artifacts somewhere. So the right trials, that will add also the full number of channels. We'll try to be very fast on here. So of course, it can be done also automatically. I will do it manually because there aren't so many. And if I do see a spike, a trial with a spike, I will just kick it out. But I'm doing this so you can see how to mark a trial with as an artifact and eliminate it. Up to now, none. My apologies. So basically, let's consider that this trial in here, it's an artifact here. So let me select artifact. We'll mark it as an artifact. You can see the label up here. So it's a left trial. I have to kick out also a right trial that contains an artifact. I think this one is a bit better, so I will unmark the other one and mark this one here because it seemed to me that it's no. I'll go back again to that one, this one here, and I have to select also for right hand. Let me go to the right hand trials. Now they are marked, they are sorted. So first we have right trials, then we have left trials according to the way I've added them to the list when I trigger the dataset. Okay, so I will take this one as an artifact, and I will just exclude the trial containing artifacts. So transform, cut trials and channels, select, and exclude artifact trials. Okay. And start. Yes. Now these two trials were eliminated, and we can go computing this common special patterns again. No, I don't want to save it. So analyze, CSP, left, right, left, 5,000, 7,000. The results. I will overwrite it. Yes, and start. Yeah, it's almost in the same way, but yeah, it looks to me that it's very good. Except we don't see exactly the spot moving around here. It's not a problem. For now, as I said, I do have to make a very close investigation or to run some other software for this, some other functions. I won't do it now because the time is not allowing us. So I will go on with the special filters. So I just created it, and now I will apply the special filter. So basically, we will extract the CSP features. Now I will browse for the file that I just created, the CSP filter. And in CSP, the most important filters are the first two ones and the last two ones. So I will create new temporal patterns. It's 1, 2, 15, and 16. And I will replace all the channels because from here on, we will play only with 4 channels. Start. And here we have the CSP for CSP features. Okay, from here on, we have to start in Motor Imagery. We're doing the variance. So I will go to parameter extraction and calculate the variance, extract the variance for all this. And I will use a variance smoothing window of 1000 milliseconds, which is 250 samples, and the overlap to 149. And replace all channels and start. Okay, here is the variance. The next step in Motor Imagery is the normalization, that we can do it from transform, arithmetic, select the norm function and start. Yes, I want to proceed. So now all these features are normalized, and then I have to apply the log 10, the logarithmic transformation, transform, arithmetic, log 10, which is the last one, and start. Yes. And this is the point where we start creating the feature matrix. So I will go to classification, feature matrix. And first, let's specify the parameters. So the classification interval will start with 500 milliseconds with a 500 milliseconds step, and it will automatically stop at 1000 milliseconds. And have to select the feature channels. 1, 2, 3, and 4. Okay, and of course, the right and left. I will save the feature matrix here with a name, test feature matrix. And we'll want to classify also this stuff. Okay, the feature matrix was created, and now the create classifier window started. So also in here, I will save this classifier, so it will be only classifier. And these are the ways we can create it in here, LDA or MDC, minimum distance classifier. So I will go for LDA, and we'll choose a train 100, test 100. And we'll map the features number 1 against number 4. Okay. And start. Now, I will get a classification dot with all the samples, windows, and so on. It's not important this, it's important the total error in here. So as we see at a certain point, it's 0%. The total error is the sum of the error rates for both classes classification. Okay, I will just keep this out. I don't need it. Cancel, cancel. So now we did create the classifier, and I will go further on applying it. So let's consider that I've took another data set, did all these steps up to here to apply the CSP filter. So I applied the CSP filter that I just created, and now I'm doing, I want to apply the classifier that I did. Okay. So classification, apply classifier, will load the classifier that I did now. So it's in feature matrix, LC, open. And in here in the right side, I do have to select the error rate, the time point where the error rate is the smallest. So we can see it's 0 at second 5. Okay, replace all channels and stop. Now we do have some other time curses. We don't understand too many things from it, but the first 2 channels are the LDA output. And as we see after the trigger, the right hand classification goes up and for the left one goes down. This is the channel, but I will show you. Let's apply a mapping on it. So classification output mapping, so we can see also the error rates and so on. I will select right and left and the first 2 channels. Okay, and start. And here we go. Basically, in this plot, we have the classification output plotted. So the dashed lines, it's the classification output for every single trial, and the solid line is the average of all these outputs. Okay, so it's for right trials, and with green we have the left trials. So basically, they have to be pretty separated from the 0 line, which is exactly in the middle. So the right trials goes up, left trials mean goes down, which is perfect. So let's go further. In the next plot, we see them individually, of course, right and left, which go up, which is normal. And in the last plot, we see the error rate. So, of course, the error rate is the sum of the errors. So now with blue, we have the right class, with green, the left class, and black, we have the total error, which is at this point at second 5 gets to 0. Of course, because I applied it to exactly the same data set, but I could have loaded another one and applied and exactly from the same user, for instance, another one, and it will look exactly the same, almost the same. Okay, so this is the classification error rate. But my session won't end up in here. So we are continuously working also on developing different ways of displaying this data, displaying results. So for instance, in the CSP part, we can see them in 3D, for instance. So I will just reload the dataset and start the common spatial patterns again. So analyze CSP and start at 5,000 and end up at 7,000. And we'll show with result 3D. We check this. Oh, sorry, forgot to set the trials. Okay, now the result to the open, displaying exactly the same plot like earlier, but now also the 3D part will start up and display some nice results. Since it's 3D with rendering, it takes a bit more longer. Mostly also zoom started. Okay, so here we go. Here we have the skull. And the very nice spot, so this corresponds to the first CSP. Let me move it a bit up. Now this display, I can switch it. So we are displaying only the 4 CSPs, the most significant ones, the first two and the last two ones. So here is the spot in here at C4, at C3, sorry. In here can be nicer seen on C3. And if we switch to the last slide, it's quite close in here. But yeah, as I said, probably it's due to an artifact. So this is only on the skull. We have the opportunity to plot all this also on the brain. So I will switch to the first slide on the C3 and I will switch the view to the brain. The brain plots. So now we have here the electrodes overlaying the brain and we are plotting everything directly on the brain. So this is the feature only for the CSP part. We have it, I forgot to close this one. We can apply it also for event-related potentials. For instance, I will load a new data set that contains my data, honestly, while I was typing on a keyboard. So I will load a data set. It's from the test data folder of g.BSanalyze that we do provide to the people, to the customers. In one moment. Forgot to close some windows here. As I said, my apologies. Zoom sometimes is slowing down the machine. So I will go to Documents, g.tec, g.BSanalyze test data EP, 8 channel EP. Okay, let me close up this window again. No, I don't want to save it. So now I will show you how the P300 event-related potential looks like. So this is, as I said, my data, it's already triggered. I did nothing to it. I don't have to do anything to it. I will only display 10 seconds of data here. And I will just fire the average window and will show you the results, the P300. So I will correct the reference interval up to 26 because we do have a baseline, which is just before the trigger, this small part in here. And I will use a statistical analysis and analyze target and non-target trials. Sorry, I forgot to click on show with results 3D. But yeah, basically this is the P300 peak. It's almost P350, honestly. But yeah, it's not a problem. I'm getting older and that's why probably the delay is a bit higher. And I will do it again also with the 3D brain, with the 3D tool. One moment, it starts. The only thing that I forgot is to load the montage. This is why it's not displayed. So header, geometry, and of course I will load the montage that we do provide with this dataset for the 300 data. Analyze this data montage. 8 channels P300. Okay, this is why it didn't work. Okay, so 1 to 26. Statistical target, non-target. I don't need statistical analysis because it's only the brain. And start. Yeah, now it will work. And it starts up now. So again, we have the sculpting here and the slider here. We can slide through the seconds. So if we have a look on this plotting here, I should move the slider. So at 0.1 seconds, we have a negative peak. Let's see. First, at 0.1, somewhere about here, at 98 milliseconds. So yes, we have this blue colors in here. Maybe it will be better if I will change the scale. So the color map, I will set it to jet. I think it will be, yeah, it's a bit better. So this is the negative peak. And we'll go to, again, a bit the right at about 340 milliseconds. Where's the peak? Here, and about in here. Yeah, in here it's better. So here we have the regions where the P3 had the highest, the activation areas, let's say so, the P3. Okay, in the same way, we can see it also directly on the brain. Okay, so here we go. So the right ones are only static views, and we can round up only the left one. And in the meanwhile, we created also a tool for, we can export all these pictures to JPEG files or whatever you want. Export graphics, for instance, a resolution 150 dpi, where we added different things. I will export it to 300. I will export, we can export all axes or only the main one, the rotatable view. And yeah, let me export it to, I don't know, first one, save, and export. And we will see in a bit when it is exported. It's done already. I have to close a image window, and I will open it outside MATLAB. So here we have the picture that I just exported. So from my point of view as a researcher, it's awesome because I can export it and add it to in high resolution for different papers, for different presentations as well. Okay, but as far as I see, my time is going up and I should start having a look on the Q&A. Okay, so.
Sound all good. I'll let you know.
Oh, okay. So basically, I just finished my presentation and yeah, I will start answering questions, but none of them.
Okay.
In this case.
Maybe you can explain a little bit your background, how you got into brain-computer interfacing and what you're doing now. So, because people are asking about which background training you need to go into BCI.
So basically, I started with g.tec in 2012. I was a PhD student back then. So I went on. I was controlling basic at the beginning, only controlling neuroprosthesis like FES and so on. And the idea of my PhD thesis was controlling a neurostimulator and neuroprosthesis via brain-computer interface. So in this way, I went to g.tec, where I found a very nice team, wonderful people in there, and started doing this with BCI. So I managed to control the neuroprosthesis neurostimulator with a BCI system based on Motor Imagery, 2 and 3 classes and so on. So since that very moment, I got amazed by BCI. I really liked this idea and remained at g.tec ever since, and doing different studies, doing signal processing, motor imagery, and so on. At the same time, I'm also working part-time at the university back in Romania. And yeah, in terms of background, this is what I did. So starting in 2012, basically I started with my PhD thesis, and then I continued with
So somebody is
mostly
asking
with
as a
g.BSanalyze.
somebody is asking as a physiotherapist if it makes sense to go into computational neuroscience as a PhD.
Basically, you need also a bit of background in terms of engineering. So I'm also an electrical engineer. I finished 5 years at Technical University in Iași. But if someone has very good programming skills, because you do definitely need a lot of experience in programming in order to do this kind of research. So if he has a bit of experience, at least an average level of coding, he could go for this. Also a bit of math, of course, because there are a lot of algorithms that need math, and then you do have to implement that math in coding. And indeed, there are a lot of tricks in order to implement different math in code, especially when working in real time. If you do want to do something in real time. Offline, you're not concerned that a lot of instructions have to be done, let's say, in 2 or 3 milliseconds. And that's the point. So, yes, but a physiotherapist would need a bit of engineering knowledge for this, for coming in here.
Federico is asking, have you given a thought on action observation with motor imagery like Rizzolatti, I think was him, observing a monkey was initially observing another person moving, and this triggered the mirror neurons. So did you ever work with action observation?
Sorry, I really didn't get the full question.
Federico is asking, you are doing motor imagery, but you could also observe somebody moving the hand. What would you get? What would you analyze?
Of course, I would analyze exactly the same things, because when seeing someone else's hand moving, you get exactly almost the same activation on the C3 or C4, on the hand projection, on the brain hand, on the cortex projection of the hands. So the synchronization appears when you are performing the movement, imagining the movement, when someone is passively doing your movement, for instance, in case of the paralyzed people, or when seeing someone else performing the movement with that hand.
Do you think this action observation gives more useful information than the motor imagery itself?
Not really. I don't think so. I never tried this, but I don't think so.
So maybe you can explain it how we are doing it in RecoverX.
So in RecoverX, the patient sees an avatar. So he sees the hands, and the cue comes up from the table instructing him that he has to move the right hand or the left hand. And in the machine learning phase, the avatar performs the movement, and at the same time, the neurostimulator starts inducing the hand opening. And the user gets as feedback after the machine learning phase, after the classifier was created. The user gets a feedback on visual feedback that the hand is moving if he imagined correctly the right hand movement or the left hand movement. And at the same time, he gets the feedback also via FAS, the stimulation of the according hand, of the right or of the left hand, according to the presented cue.
The Peter is asking students who have a neurodiagnostic degree, which want to go into the PCI field, what is the best way of doing it?
I think they have a bit more, they are a bit more luckier than physiotherapists. Because having this degree already in brain sciences or something like this, I think they also have performed a lot of research previously, and I think they can do it from my point of view.
Okay, so thank you very much. This was very nice.